But before we go all the way into that, we're first going to do more of this radical review that I kind of talked about during our warm-up today. The square root of 8. Square root of 8. Square root of 8 is can we make it the square root of 4 times the square root of
2.
Square root of 4 times the square root of 2.
Wait, how can we make it the square root of 2? 2 doesn't have square root.
We can make it the square root of 4 times the square root of 2. So 2 does have a square root, it's just not a perfect number. It's like 1 point something, something, something. It's not a perfect number though. It's not another whole number. So we don't say it's a perfect square, but it does still have a square root. It's not a whole number. Now we say it's equal to the square root of 4 times the square root of 2, because if we multiply these numbers underneath the radical, we go back to the square root of 8. Okay? So, square root of 4 times the square root of 2. What is the square root of 4 equal to? 2. What kind of 2? Do we write square root of 2?
2.
No, we just write normal 2. Okay? The common misconception is we'll still write square root of 2, but it's not a square root anymore. It's normal 2. We did this operation. Think of it just like adding or subtracting or something like that. After you add two things, do you still write the plus sign in the middle? No. So after you square root something, you don't write the square root symbol. You don't write it anymore, but we still have this square root of 2 over here, and they're still multiplying together. And we can't simplify this anymore because we cannot break the square root of 2 down into any more perfect squares. And right above this, it says check for perfect squares, and hey, look, it lists the first 15 perfect squares for you. 1 squared, 2 squared, 3 squared, 4 squared, so on and so forth, all the way up to 15 squared. What a real G. Right? Okay.
Do you know all of them?
I know up to 25.
What's 25?
625.
Wait, 625?
Yeah, it's 25 squared. But square root of 108. Square root of 108. What we want to look for is we want to look for the biggest perfect square that goes into it. We could do it with smaller ones, but it's going to be more work. We can get there still. Abby, you had your hand raised. What are you thinking? Right. So 100 is the biggest square root that's still smaller than it, right? The biggest perfect square that's smaller than it. Is 100 a factor of 108 though? No. How can we check it if we don't know? Okay, we could do our calculator.
81.
What could we do in our calculator?
14.
Type in 108 divided by 100 and see if it goes in evenly. It doesn't, but we could do that, okay?
81, right?
It doesn't, but we do that. Does 81 go in evenly to 100? 108?
41.
Okay, take a calculator, Randall, and take 108 divided by 81. Take 108 divided by 81.
Wait, Mr. Hawson.
Yeah.
So, basically, we could just divide that number by every single number up there.
And see what goes into it evenly.
And then find our answer.
I got 1.
108 divided by...
Yeah, I reduced to the nearest.
Oh.
No. Okay. Does 108 divide evenly by 100? No, so that one doesn't work.
64.
Does 108 divide evenly by 81? No. Nick, what are you thinking?
Actually, could I please get a?
Oh.
Oh, yeah, no problem. Thanks for saying something, buddy. Okay,
No problem.
Abby.
Can you do the same thing you did for A?
Okay, what? What two things can multiply to 108?
10 and then 4.
36 if I'm the winner.
10, 4, and 2.
You said 10.
Okay, so here we didn't add 2 and 4, though. We multiplied them. So we need things that multiply to 108. 10 times 4 times 3 is not equal to 48. Okay, what's 10 times 4, Abby?
No, 10 times 10. Wait, 10 times itself.
Okay, what's 10 times 10? 100. Can 100 times anything get 108? No, so it won't work. Okay, Randall.
36.
36! 36 times what was 108?
3.
3. How could you know?
I used my.
What operation did you do in your calculator? Marley said it?
Division.
Division. You did 108 divided by 36. Randall guessed and checked and it kept going down and said, hey, we have a winner. 108 divided by 36 is 3. So that means the square root of 108 is the square root of what times the square root of what?
36
36 times the square root of 3. Why do we want to choose the square root of 36? Why is that our option?
It's perfect.
It's a perfect square. What is the square root of 36?
6.
It's normal 6. We want to get whole numbers out here. We want to get whole numbers out here. Square root of 3. Does square root of 3 become any other number? Is it? No, there's no perfect square smaller than it besides 1, and that won't help us. Yes, Nick?
Does it matter the order we put it in? Or
Like if you had put 3 and 36?
yeah.
So Nick asked a good question. Could we put the square root of 3 and then the square root of 36? Yes, you could, but when you get it down to this step, we want our normal number out in front. Okay? So you'd have to switch it around here. That's a good question. Okay? Now I heard Nathan saying something to the effect of, what about on this one, we did this one, this is extra, you don't have to write this. Extra, don't have to write it. What if we had the square root of 108, and that would be the square root of 54 times the square root of 2. That's what Nathan was saying, those are two factors. Is 54 a perfect square?
No.
Is 2 a perfect square? No. So that one wouldn't help us too much. Okay? So that one wouldn't help us too much. Thank you. So that's why we don't want to choose that one, okay? Good, thank you. Randall, do you want to check if square root of 9, if 9 goes into 108? Take 108 divided by 9, see if it goes into that.
That's why I said 81, I thought 9 was 81.
Does 108 divided by 9 evenly?
What?
Just take 108 divided by 9.
Oh, yeah, 12.
Okay, so we could have also said, just listen to this, don't have to write this part down, just listen to this one. We could have also said the square root of 108 is the square root of 9 times the square root of what, Randall? 12. And the square root of 9 is exactly what number?
3.
3, because 3 times 3 is 9. Square root of 12, is there anything times, are there any perfect square factors of 12? I heard a yes. What are you thinking? 4. 4 times, so it's 3 times the square root of 4 times the square root of 3. So after we do the process, if we don't get the biggest perfect square, if we get a smaller one, we can still be on the right path. We have to keep going. We have to keep going. What is the square root of 4?
2.
And this operation is still multiplication. And so what is 3 times 2?
6.
Did we get the same answer? Yeah. This is a long process this way, right? So if we find our biggest perfect square, we get a shorter process. But if you find smaller perfect squares like 9, you notice 9 first, you can still get there. You just have to do this process a second time with smaller numbers. But sometimes that's easier for us to see. Want us to look at letter C real quick? Let's look at letter C real quick here. 4 times the square root of 125.
25.
Okay, so try. Yes.
Are we taking like the numbers like A, B, C, those numbers, and dividing by the numbers above that to like see which one is?
Okay. Yeah. Yes. Yeah. So we're taking these. What's underneath the radical? We're taking what's underneath the radical, and we're seeing if one of these perfect squares, because these are different perfect squares, is a factor of it. So we're looking for factors of these that are perfect squares. So 4 is one of these. 36 is one of these. So you want to take 125. And you want to divide it by these numbers and see which one works out perfect. Works out evenly, okay? Now, would it be reasonable for us to clear out 196 here for this one? Why not? It's too big. What might be the first number we want to start at?
I say 25.
Okay, what's the first number smaller than this, though?
100.
121 is the first number smaller than this. But it won't work. So then you can try 100. Then you can try so on and so forth, and keep trying so that way you make sure you get the biggest one. Gracie, what's your question?
Then where do you get the times 3 and the times 2?
So 108 divided by 36 is 3. So that means 3 times 36 is 108. So the factors of 108 are 3 and 6. Just like the factors of 8 are 4 and 2. Does that make more sense?
Sure.
Are you just saying that?
No.
Okay. Thanks for asking. So, Randall, you said you had an idea of something of a perfect square factor of 125.
Yeah, I don't know if the 4 is.
Okay, the 4 is out in front being multiplied with it. So we're just going to keep writing it for now. 4 times 5 times.
Yeah, 25.
25.
Alright, so the square root of 25. What's 125 divided by 5? 125, excuse me.
Wait,
What's 5?
4 times the square root of 25? Is that
4
25?
times the square root of 25 times the square root of 5. Because we're saying the square root of 125 is the same thing as 25 times, or square root of 25 times the square root of 5. Because if we look at the numbers underneath the radical, 25 times 5 is 125. This times this is this. So that means this is the same thing as these two things times each other. Wait there. And we just have this 4 being multiplied with all of this, so we just keep writing it. We just keep writing. We're dealing with what's underneath the radical right now. Okay, so where do you get that 5 from? The square root of 25 is 5, because what times what is 25? 5. So this is like 4 times 5, and the square root of 5, because we still have the square root of 5 because we haven't done anything with it. We do the square root operation on our perfect square, get 5. So so what can we do with this 4 and this 5? What sign between them? Multiply them. 4 times 5 is 20. And we cannot simplify the square root of 5 anymore. If we look here, square root of 5 would fit in here. Does 4 go into 5 evenly? No. And we don't even want to worry about 1 because we'll just get 1 and 5 and that won't help us at all. It won't get it any smaller. So this would be our answer. So when we're looking for factors, we only look at what's underneath the square root. We only look at what's underneath the square root when we're looking for factors, but we continue to write it down. We don't get rid of it, we just don't look at it for the very first step. Square root of 3 times the square root of 2. When we multiply radicals, we want to look at we want to multiply the numbers inside. So just like the square root of 25 times the square root of 5 is the square root of 125, what's the square root of 3 times the square root of 2 going to be? Square root of 6. Multiply with what's underneath the radical with what's also underneath the radical, and it stays underneath the radical. That's what we call this thing a radical or square root.
Yep.
Randall?
When will we have this test?
I don't know off the top of my head. On E, 3 times the square root of 5 times 7 times the square root of 5. Now, we can't condense a number outside the square root with the number inside the square root anymore. But what can we multiply the 3 with here? 7. And what is 3 times 7?
21.
21. And what is the square root of 5 times the square root of 5? 21. The square root of 25. And so we multiply what's not under the radical, what's out in front, with what's out in front, and what's underneath the radical with what's underneath the radical. So we multiply the like things together. Multiply the normal numbers together and the radicals together. Nick.
Don't we simplify from here?
Awesome. What can we simplify from here?
25.
What is the square root of 25?
5.
5. So this is like the same thing as 21 times 5. Instead of 21 times the square root of 5, the square root of 25 is really just 5.
Just keep it 5 there. Without doing 25, just keep it 5 there, right?
If you catch that, then yes. Okay. And 21, because that's what we're doing here, is this is multiplying with this, which is multiplying with this, which is multiplying with this. Yeah, so we multiply 21 times 5, which gives us 105.
So that would be our answer.
Yes, because we can't simplify 1 of 5 anymore. It's already 1 of 5.
Oh, it's complicated.
What?
Are you trying to make it to where there's no this?
No radicals?
Yeah.
If you can, but sometimes we have them,
Yeah.
and that's okay.
So the
We want to get it down to the smallest in there we can. And in some cases, we completely get rid of it. Because if there's a perfect square, we can completely get rid of it.
So the radicals, the houses.
So what's it mean? Yes, the square root thing, it's called a radical. Okay, it's called a radical. What's it mean to square something? It means to the power of 2. What's it mean? Multiply it by itself. It's this many, however many is the exponent, this many of these in a row. So there, it's the same thing as 9 times the square root of 2 times 9 times the square root of 2. Is this pretty similar to E now? Now that we wrote it like this, it's pretty similar to this, 2 of these in a row. But these are just 2 of the same thing, because the exponent just means 2 of these being multiplied together. So we take the 9 times the 9, the numbers outside the radical, and get 81. And you get square root of 2 times the square root of 2 is the square root of 4. Hey, which is a perfect square. So what is the square root of 4? 2. Normal 2. And 81 times 2 is?
162.
162. Okay. Now, we said when we square something, it's like we're multiplying two of them in a row, right? Okay? So that means like here, this is like the square root of 5 times the square root of 5 would be like the square root of 5 being squared. And little aside, let me write this up here. If we have the square root of, I'll do a different number, square root of 3 times the square times the square root of 3, square root of 3 times the square root of 3, would that be the same thing as saying it's the square root of 3 but being squared? Because that's all this is saying is we're multiplying two of them in a row, right? Okay? But if we solve the square root of 3 times the square root of 3 times the square root of 9, and what is the square root of 9?
3.
So here, when we see a square root and a square, those kind of sound similar, a square root and a square. Okay? Those are what we call inverse or opposite operations. So addition, what's the opposite of addition? Subtraction. They're called opposites. They are inverses. They undo each other. What undoes multiplication? Division. So a square undoes a square root, and a square root undoes a square. So whenever we square a square root, we just get what's inside. Whenever we square a square root, we just get what's inside of it. Okay. Now we're going to go to some newer stuff. So right below this, right triangle. A right triangle is a triangle with one right angle. Refresh my memory. What's the measure of a right angle?
90 degrees.
90 degrees. Awesome. That's some good class participation on that. I'm proud of you guys on that one, okay? So, if we call these sides A, B, and C, we'll call A and B the legs. We'll call A and B the legs. Does anybody know how we can tell which ones are going to be the legs?
Because they're not slings. They're connected to the square.
They're connected to our right angle here, right?
They're holding them.
You can think of it as we're holding it. So like legs hold up something, or like legs hold up the desk, or like a table. The legs are kind of like holding up the right angle. If that's helpful to think of it that way, I haven't heard that one before. I like that. Okay? So A and B are our legs. Does anyone know what we call C?
Hypotenuse.
Hypotenuse. Hypotenuse. Hypotenuse. Okay? Now, how can we tell which one's going to be the hypotenuse just by looking?
It's across from the
That's the longest one.
What do you say?
It's across from the right.
It's across from the right angle. Is this one touching the right angle? No, but the other two are. So the way we can always know is this going to be across, this is a parenthesis, across from the right angle. Ooh, I just butchered the right. Maybe.
I know.
Okay, and Max had another interesting fact about this. Max, what interesting fact did you say about the hypotenuse?
The square is pointing at the hypotenuse.
Okay, okay, you can think of the square kind of pointing at that. But you also said something before that. It's the longest side. Okay? But it's also the longest side. So that's another good thing to remember is the hypotenuse will always be the longest side. 100% of the time, the hypotenuse will be the longest side of the right triangle. It's always going to be longer than the length. Not the same length, not less, always longer. So we have this Pythagorean theorem. We talked about this a little bit, and we've used it a little bit, right? Last chapter we just used it a little bit. Okay? In a Pythagorean theorem, it says in a right triangle. Do we have a right triangle?
Yes.
Yes. If the legs have lengths A and B, does this leg have a length of A?
Yes.
Does this leg have a length of B? Yes. If the legs have length A and B and the hypotenuse has length C, does this hypotenuse have length C? Okay, then we know that A squared plus B squared is equal to C squared. So what this is saying is that if you square the length of the leg and you square the length of the other leg and add them together, you'll get the squared length of the hypotenuse. Okay. I cut off quite a bit from before the, it's not don't do's, but I cut them off. So if you flip the page, let's look at example 1. What kind of triangle do we have?
Right
A
triangle.
right triangle. That's going to be a continual thing in this chapter. We're going to have right triangle after right triangle after right triangle, okay? We have a right triangle. What two lengths do we know?
Leg is leg.
5 and 12, which are both legs. Very good. We know the leg and we know this leg. What is x?
No,
The
no.
hypotenuse, and we don't know it. So we're trying to find the hypotenuse of the triangle. How can we find the hypotenuse if we know two of the legs? A squared plus b squared equals c squared. What's our a and b?
5 and 12.
Does it matter which one of these is a and which one of these is b?
No.
No. What do you want to call a, Kennedy? Okay, cool. So that means b is 5. Awesome. So let's put 12 squared plus 5 squared will equal our x squared, which is our unknown one. 12 times 12 is 144. So I put parentheses because if we put a negative in there, which length can't be negative,
51?
okay? You don't have to. Okay, I always put in parentheses when I substitute. I do it. What is 12 times 12? 144. What could we, if we don't know that, what could we do? Type in the calculator. What's 5 squared? 25. It's funnier than 24. And x squared will stay as x squared. Can we continue to add these two? Let's look to continue to add them. 169 equals x squared. You could also call it c squared. You could call it whatever, okay? So now, once we have 169 is equal to x squared, we want to know what actual x is, though. So we need to, how do we undo the square? We square root it. We say this undoes it. And if we do it to this side, just like whenever we add or subtract or multiply, we have to do it to both sides. So we say the square root of x squared, those undo each other, so we're left with whatever's inside. So we're just left with x. And what is the square root of 169?
Oh, it's
13. It works out evenly. So the length of the hypotenuse of the right triangle is 13. Good talk. When one of them get back. Okay. We also have these Pythagorean triples. A Pythagorean triple is just going to be a pattern we recognize, okay? You don't have to use them, but they are a pattern you can recognize, okay? So if you catch these patterns, this is something that can help you, okay? If you catch these patterns, this is something that can help you. So it's a set, they go together, of 3 positive integers, just numbers, that are whole numbers, that form a right triangle. So some common ones are where two of the legs will be 3 and 4, the hypotenuse will be 5. If the legs are 5 and 12, the hypotenuse will be 13. If the legs are 8 and 15, the hypotenuse will be 17.
Like last.
It always works out that way.
Like last
And-
problem was 5 and 12.
The last problem. The last problem was, what were the two legs? 5 and 12. So according to this triple, because the smaller two sides are 5 and 12, what's the longer side have to be? 13, and the hypotenuse is the longest side. So we could have known, if we knew this, and we recognized this, we could know, oh, 5, 12, the last one has to be 13 without even doing the theorem. These are our most common ones.
Easy peasy.
And you can also do multiples of them. So you can do a multiple of them, so we can do 6, 8, 10, or 9, 12, 15. How did I get 9, 12, and 15?
You just kept multiplying.
Multiply by 3.
So if you just memorize them, you don't ever have to do work. If it's like that.
If it's like that. Yes.
That's easy.
If you catch those. And they won't always be Pythagorean triples, but if you catch them,
I would always catch them.
catch me outside. How about that? Okay.
How about that? Hey. I know that, right?
5, 12, 13 is one of our triples. So if you see 5 and 12, then you know the hypotenuse has to be 13, but only if those are the two legs. So it only works when those are the smallest two, on the first two, and the hypotenuse is the longest one. Okay, example 2 here. Example 2. Find x and write our answer in simplest radical form. So it might not be a whole number, but we don't want to put the decimal in. We want to find our answer in simplest radical form. Now, we have enough information to find this side right now?
Can you put that thingy over there?
What thing you over where?
You don't know if they're the same, you know, that triangle? The little thing? Right there.
Would it just be 20?
Keep going on the other side.
This? Yep, this is also 90 degrees. So does that tell us that this is the right triangle?
It's gonna be 5,
How do you know this might be 5?
because look at the common thing.
Okay, so what are you noticing here about
Not that
5?
one.
This one?
To the right.
This one?
Yep.
Okay, so do you see a 5 and a 13 here?
It'll be 8.
Okay, you're thinking it might be that. Okay, you're guessing, you're hypothesizing here. You're guessing. Alright, let's first say, in order to find this side, we need two sides of the triangle. So we need this side and we would need this side of the right triangle in order to find the hypotenuse, right? If we were just given this here, this triangle here, pretend like you can't even see this over my paper, even though you can. If you're just given this, you would need this side and this side to find the hypotenuse, right? So that means that we need to find what this length is in order to find this. Can we figure out what this length is?
Oh,
How?
Opposite.
Could we figure out, could we do the document theory here?
Wait,
The
maybe.
opposite. It just makes sense.
Okay. Okay, this is a right triangle, right? Here on the left. This is the right triangle. Okay, is this a leg or hypotenuse? Is this leg or hypotenuse? Is this leg or hypotenuse? Okay, what do you want to call this? A. Awesome. Okay, what do we call A? So if we were to set up a Pythagorean theorem for this triangle to solve this, we'd have a squared plus equals 10 squared. Notice the hypotenuse still has to go by itself, and our legs still have to be on the left side. The hypotenuse has to go by itself on the right side. The legs still have to be on the left side here. So if we do this setup here, we can't do 6 squared plus 10 squared because 10 is the hypotenuse, so it has to go on the right side by itself. So what's a squared? Well, it's just a squared. What is 6 squared? What is 10 squared? 100. We need to get a squared by itself, though. We will subtract 36 first. Get that away from there. 36 minus itself is 0. A squared is equal to 64. So now that we have the squared equal just a number, we need to say we need to get a instead of a squared. How do we undo the square? Square root it. So a is equal to, what is the square root of 64? 8. Kylie, how did you know this was 8 earlier? It's this triple, right? It's 3, 4, 5, but the multiple is 6, 8, 10. So you saw 6 was a leg, 10 was a hypotenuse. So this one has to be 8. Catch that, that can save us some work. But now we need to find this x, right? Okay. How can we solve this x for x here? 8 squared plus 12 squared is equal to x squared here. This leg plus this leg squared plus this leg squared is equal to hypotenuse squared. So then you take 8 times 8, which we said was 64. We said earlier, last page, example 1, or I guess this page, still this last slide, was 144 is equal to x squared. If you don't know what 64 plus 144 is, you can add it off to the side, put it in your calculator. We'll get 208. How do we get x squared just to be x? If we square root this side, what do we do this side? Square root it, so after we do all the adding, we do that. So x is equal to the square root of 208. Is 208 a perfect square?
No.
Or that means we need to. We need to look for our perfect squares. We need to look for our perfect squares and simplify it. So what are 2 factors of 208 where one of them is a perfect square? So bust out your list. Okay, does 100 divide evenly into 208? Darn. 4 works. Okay, 4 times what? 52.
52.
So this is the same thing as the square root of 4 times the square root of 52. Square root of 4 is normal 2. Square root of 52, I think there's another perfect square inside of that. Let's look for another perfect square inside of the square root of 52. Another perfect square is a factor of the square root of 52 because we can still keep going. 2 is not a perfect square. 16 does not multiply into 52.
I'm gonna guess.
4.
Square root of 4 times the square root of
20.
13. 26 is a factor, but it's not a perfect square.
2 times 2.
So, what is the square root of 4? 2. So 2 times 2. The square root of 13 does not have any perfect square factors. 13 is a prime number, which means the only factors are 1 in itself. We take 2 times 2, which is 4, times the square root of 13. So x is 4 times the square root of 13. So when it asks for simplest radical form, this is what it's asking for. Where you solve the radical in there sometimes unless it's a perfect square. Like a,
So do we have to do this much work for every single pattern? Yes, so much easier.
not necessarily.
That's what I'm saying.
Okay.
More time. This was easy.
I'll get the
If this was
6,
3,
8,
when am I gonna need this time?
Did you through high school?
What?
what?
Up here. Triangle. Look. 5. Well, that means this one's gonna be 13.
It's just common scenarios that we see. So here, this one was 6, 8, and 10, so they were 3 whole numbers, which is a multiple of this. It won't always work out that way because this was 8, 12, and 4 times square root of 13. That's not one of them. But these are common ways they can be shortcuts for us if you catch them. If you don't catch them, you can still do the math, but they can be common shortcuts for us. Alright. Do you guys remember back when we talked about angles and sides of a triangle? We said, hey, the smaller an angle is, that means the side opposite it's going to be smaller or bigger. Smaller. Remember when we ordered our angles and our sides from like smallest to largest?
Oh,
Okay? And the smallest angle was across from the smallest side, the middle angle was across from the middle side, the largest angle was across from the largest side. You guys remember that? Okay, there's a correlation there, okay? The bigger the angle, the longer the side. Okay? Think of it kind of like a flashlight, okay? If you reduce the light, it just goes to this little thing, it's not going to shine a very wide thing. But if you let it go out, have a bigger angle, it's going to shine wider across. It's going to be a longer place that it shines. Okay? So, we can think of that also with this converse of the Pythagorean theorem. We'll talk about that a little bit. We're going to skip example 3 for now.
cross it out or not?
Don't cross it out. So go ahead and flip your page to the converse. So this can be used to check if it's a right triangle, or we can figure out if it's obtuse or acute as well. So we're saying if 3 sides of a triangle, if we don't know it's a right triangle, but if we see 3 sides of a triangle, we can check to see if a squared plus b squared equals c squared, then the 3 sides will form the right triangle. So we can check, does it equal it? And I'll talk about these 2 things here in a second. I'll talk about those 2 things here in a second. So here on example 4, we're supposed to tell whether this is the right triangle or not. We don't have a box here to tell us. We just have these side lengths. So how could we plug this into our Pythagorean theorem to see does it equal? Does it work?
20 squared plus 11 squared.
Okay, so we call like this our A, this our B, and this our C.
Yeah, and then I would just put c squared and then figure that out.
So say, does this work? Or you can figure out what c squared is and do the math too and say if it's equal. You can do that. So we say, okay, we set it up as if we were doing the Pythagorean theorem, but we actually know all 3 numbers, and we say, okay, let's see if this works though. Let's see if it works. We're not undoing it, we're checking. Okay, we're saying, hey, does this work? Is it a right triangle? Because if it satisfies it, if a squared plus b squared is equal to c squared, if this plus this is equal to this, then yeah, it's a right triangle. If it's not, it's not. 20 squared is 400. 11 squared is? What is 23 squared?
521.
Ooh, nice, 529. 400 plus 121? Does 521 equal 529? No, so is this a right triangle? No, it's not a right triangle. So the answer is no, not a right triangle. Not a right triangle. And we know that because it did not satisfy this. Now here, what was bigger, c squared or a squared plus b squared? C squared. So that means if c squared is bigger, that means that this side must be too big for it to be a right triangle for the given other sides. That means this side must be too big for it. So if this side was too big, does that mean the opposite angle is too big or too small?
Big.
Too big. So we said the smallest angle is across from which side? Smallest side. The biggest angle is across from the biggest side. So here, if this angle got bigger than it should be, if this is bigger than it should be, if c squared is bigger than it should be for this to work, then it's going to be obtuse. If c squared is greater than the a squared plus b squared, it's obtuse. Whereas if c squared were to be smaller, which is not on this one, if c squared were to be smaller, this side is smaller, then it's acute. So I would want you to write, yes, it's obtuse. We'll be practicing doing that. That yes, it's obtuse. Because c squared is bigger. And I want us to think of it as it opens up. It has to open up bigger to a bigger angle than it was in order for this side to be bigger than it would be for a right angle.
How do we know which side's A, B, and C?
So the hypotenuse has to be the longest one, right? So we know that has to be c. So what's our longest here? 23. So that one has to be our c. It doesn't matter which one we call A or B. No, we can interchange them. So does that make sense? Great question. Thank you for asking that, Marley.
How'd you get 521?
400 plus 121.
Oh, okay.
Okay. I'd rather you ask than not. Okay. Example 5, real quick. Okay. Example 5. Can segments of lengths 11.2 inches, 6.5 inches, and 7.1 inches form a triangle? And if so, what type?
I know.
Ooh, we checked back in chapter 4 on whether or not 3 segments could form a triangle based on the lengths. We checked back in chapter 4 to see if 3 lengths could form a triangle. Does anyone remember how we checked that?
Oh, I remember checking.
It was something with the smallest 2 compared to the largest 1. It's something compared to the smaller 2 compared to the third one.
If it goes.
What are their smaller 2 angles here? Or smaller 2 sides?
Oh, can we just do what we just did?
We add them together, don't square, we just add the smallest 2 sides, and this is to check if it's a triangle. This is to check if it's a triangle. We've done this part before from chapter 4. This is checking if it's a triangle. We take the smaller 2 sides, 6.5 and 7.1, and if they add up normally, not squared, normally, to be bigger than the third side, then it'll work. So, we say, is this equal? We don't know. We want it to be bigger. So what's 6.5 plus 7.1?
13 points.
Is 13.6 bigger than 11.2?
Yes.
So our answer to this first question is yes, it is a triangle. They can form a triangle. Go check. Yes. So to find out if the acute, obtuse, or right, we have to check our a squared, b squared, c squared thing and see if c squared is bigger or smaller or the same. Which one's our biggest side? Yep. And because our biggest side has to be our hypotenuse. Yes. Okay. So we do this part without squaring them, just to see if it's a triangle. This was from chapter 4. We say, okay, if these first 2 sides of the smallest 2 sides add up to be larger than the third side, it'll make a triangle. If it doesn't, it won't. Then, by our converse of the Pythagorean theorem, we're going to try and figure out what type of triangle it is. Since we know it does make a triangle, now we can figure out what type. And we're going to do that by doing these 3 numbers, but instead of just adding them together normally, we're going to add them together squared. And we do that because it mimics our Pythagorean theorem. It mimics or is similar to our Pythagorean theorem. So it means that there's going to be more to follow. A semicolon in English means that, hey, I'm not quite done with the sentence, there's more to follow.
We're learning about that like right now.
Oh, pretty neat. Cross curriculum.
Just testing you, making sure you know what it means.
Oh, you're
Okay.
I got 42.
Okay. So,
What are you doing?
I don't know if it got your attention. So we do this because it looks similar to this is like our Pythagorean theorem, but this time we're saying, are they equal? Because if they are equal, it's a right triangle. If they're not, then that means it's either obtuse or acute, and we can figure out which. So So we take 6.5 squared, and we'll get 42.25. 7.1 squared, 50.41.
225, and then equals, stop. Why do we?
Oh, my bad. I put too many twos there. You're right.
Oh, I wrote it in pen.
42.25. Guys, stop the side chatter. 11.2 squared is 125.44. Nick.
We have
We
5
have
minutes.
like 5 minutes left.
Oh. Times about 2.
Okay.
So then you would add the numbers together.
So we add these together.
Wait, why is 50.41 still squared?
That's a question mark.
Oh,
And is this equal to 125.44?
No.
No. What is it compared to it? Less than or greater?
The 1.125.
Yes. So our c squared is greater.
It's up to.
So it's up 2. So if we go to our little cheat thing up here, c squared being greater than a squared plus b squared means it's an obtuse triangle. Means it's an obtuse triangle. So it doesn't make a triangle, yes, by this first check. What kind? By the second check, we know it's obtuse because c squared is bigger than a squared and b squared added together.
Plus
Interneath.
100.
If I pass my final, can you grade your out whenever before I play it? And I won.
I'll
Throw
consider
it
it.
out until
Okay.
yes.
Hey, I want to quick talk about the setup on 6. We're not going to solve this one, but I want to talk about the setup on 6 real quick. So please buckle up and listen with me here real quick, okay? Buckle in, listen with me real quick. Same question here. Can segments with these 3 lengths instead of those 3 lengths form a triangle? If so, what type? The first check if they form a triangle, we need to add the smallest 2 sides together and see if it's bigger than the third side. Right now, do we know which 2 of these sides are the smallest, which one's the biggest?
No.
No, because we can't compare this with the others, right? Could we type this in a calculator and figure out what it approximately is so we can compare? Let's do that. So in a calculator, 2 times the square root of 41 is approximately 12.8. So which one of these sides is the biggest? 12.8. So this one. So which 2 would we add together then? 8 and 10. And we compare it, we say, is it equal to? And for this one and this one only, it's okay for us to say 12.8. So is 18 bigger than this? So it doesn't make a triangle? Yes. If it's bigger, it makes a triangle. What I want to key in on here is when we go to check what kind of triangle, we aren't going to finish the check what kind of triangle, but when we go to check what kind of triangle it is, you will use this one, the exact, not our approximate. You will use the exact, not the approximate.
So what is that?
We have homework.
Yes. Listen up right now. So when we go to check this, we'll take 8 squared, the small, plus 10 squared, and say, is it equal to the actual side length, not the approximate, 2 times the square root of 41 squared. Making sure we square the whole thing here. I want you to write this part down that I did in the orange. I want you to write that part down that we did in the orange. And if we ended up solving it this way with this number, with the actual radical, we would get that it's a right triangle. If you do it with the parenthesis, you get that it's not a right triangle.
Equals 2 times 41 squared.
2 times the square root of 41, which is all being squared. Okay. Now on this homework, there are not don't do's, but it was originally like 3 pages or 4 pages, but I cut it down to 2. So it was originally like 30-some problems, but I cut it down a lot. I just didn't want to print them extra and have to cross them out. If you put this in a calculator, just square root of 41 times 2.
Is it possible you don't?
Okay. Hey, when is this going to be due?
Friday.
Friday, which is our next class. If you have questions, what can you do? Ask me. Study hall.
Can you put me on study hall?
If you want to be on my study hall list, come back to my desk. Also, did somebody lose a silver necklace chain thing?
Me.
Yes.
Is there gonna be a lot of freshmen in here?
Yep.